Nice, Martine. Can you hear me okay? Yeah. So I should go to my room, you're saying? Yeah, but I'm going now. I'm live broadcasting to soon. Well, it's right now 7:30. We've got two folks watching. Um, no, I think we'll probably give it a couple minutes for more to join, besides just those two. Then we'll get started. While we wait, if there's anything you particularly want me to cover or you were confused about on the review, go ahead and let me know about it in the chat. Got three of us now. Four. That's better. 6 of you. Who's here? Can you all hear me? Seven of you. How's the sound? Can everyone hear? I know Martine could hear me, but I'm not sure about anyone else. Does the sound still fine? Hopefully, yes. I should see you guys in the chat. You guys not chatting? There we go. Hey, Kayla can hear. Good. Cool. Well, as long as we're still good on the sound, I think I'll go ahead and get started. There we go. Now I can see you. I was worried for a second. Well, again, I'm going to go through and do the review problems one by one. If you have questions, let me know. If there's anything I should cover in more detail, let me know. If there's anything specific you want me to cover, because I might not get to everything in the hour and a half we have, then you should let me know. Otherwise, I'll just start at the beginning and go one by one. All right, starting with number one. Explain why we have replaced our first definition of the sine ratio, which was sine of A equals side opposite over the hypotenuse in a right triangle, with our new definition, which is now sine of A equals y for the point xy at which the angle A intersects the unit circle. So we used to say this, and then now we've got this. And here it was sine of A equals that. And here we've got Here's again angle A, and sine of A equals y. And the reason we made that change was because the old definition, this one's the old definition, was only useful for acute angles of right triangles. So it had a limited domain. Domain limited to 0 less than A less than 90, or 0 less than A less than pi over 2. Here, domain is A such that A equals all reals. Domain here is not limited. So on the unit circle, we can now have angles that go past 90 degrees, and we could also have negative angles. In a right triangle, we don't have either of those. Can't go past 90 degrees, can't go negative. That's why we change definitions. Cool. If I don't see any questions on that, I'll move on to number 2. Okie doke. Starting from the point 1, 0. So y-axis, x-axis, 1, 0, and proceeding counterclockwise. Counterclockwise. The points A, B, and C have been marked on a unit circle. This is the unit circle. Each an arc length of 2 units apart. So we've got 2 units, point A, then 4 units, point B, and then 6 units, point C. So that was 2 units, 2 more units, and over to here, 2 more units. So here, theta equals 2 radians over here. Theta equals 4 units, and let's see, another color all the way around to there. Would be when theta equals 6 units. So the idea here is that you have to actually understand what the unit circle is and what a radian is. And if you do, you'll know that the unit circle, every unit is 1 radian because the radius is 1, and that's what a radian is. And you also know that on the unit circle, the xy coordinates are the sine and cosine of the angle. So if the angle is 2, then the xy coordinates for point A are going to be sine, oh sorry, x is cosine, are going to be cosine 2, comma, sine 2. And you will know that for point B, we'll be at 4 units and 4 radians, so cosine 4, sine 4. And for point C, we'll be at cosine 6, sine 6. So it said round to the nearest hundredth. So I'm going to pull up a calculator. And find cosine 2, sine 2, and this will work much better if I make sure my calculator is in radian mode. So the first one is point A at negative 0.42 and 0.91. Then point B, which will be at cosine 4, sine 4. So negative 0.65, negative 0.76, and point C, which is at cosine 6, sine 6. So 0.96, negative 0.28. There's the answer. Unless I see some questions in the next few seconds or so, I will move on to number 3. I guess just because it's worth noting that since I am in Desmos, that we could actually see this really clearly over here. If I graph the point cosine 2, sine 2, and I label it point A, and I could graph the point cosine 4, sine 4, and I could label it point B, and I can graph the point cosine 6, sine 6, and label it point C. And we can see rather clearly that all of those points are on the unit circle, that circle. Cool. Okay, number 3 says, place the following unit triangles on a unit circle. So there's a unit circle. And I want to start with a triangle with a side length of sine pi over 6. So I'm going to say pi over 6 is like 30 degrees. So I'm going to go over here 30 degrees. If I want the sine to be, if I want the sine of pi over 6 to be one of the sides, I remember that sine is opposite over hypotenuse. So if I make the hypotenuse equal to 1, this is 1, then this side here will be the sine of pi over 6. Because that angle is pi over 6. So here I'm saying I know that sine is opposite over hypotenuse. And if the hypotenuse is 1, then sine of pi over 6 equals opposite over 1, which is just the opposite. So I made the opposite side be the sine of pi over 6 by making the hypotenuse 1. Obviously, since the hypotenuse is 1, it is on the unit circle, because the unit circle has a radius of 1 unit, which is why we call it the unit circle. Cool. That one was in red. Now in blue, I want a triangle with a side length of tangent 3 pi over 4. Well, I remember that tangent is the opposite over the adjacent. On the unit circle, that's the y over the x. So if I'd like the y value to be the tangent of 3 pi over 4, I'm going to make x equal to 1. So I'm going to go over here, make the x value equal to 1, and I'm going to make an angle of 3 pi over 4, which comes around like that. And I'm going to make a right triangle. So theta equals 3 pi over 4. And right triangle, just like this was a right triangle. And because this is 1, which means it's on the unit circle, because the unit circle has a radius of 1, which is why we call it the unit circle, then this side will be tangent of 3 pi over 4. Now, I might remember that this is negative 1, which means that this is negative tangent of 3 pi over 4, in fact. Last one, which I'll do in green, cosecant of 5 pi over 3. So I have to remember that the cosecant ratio is the reciprocal of the sine ratio, which is hypotenuse over opposite. So if I want the opposite, which is the y value, to be 1, so that the hypotenuse can be this cosecant, I'll make the y value at 5 pi over 3 radians equal to 1. So I'm going to mark out here 5 pi over 3 radians, which looks like that. And then I'm going to make the y at equal to 1. And it'll stick out here like that. And here, the y value is negative 1. And the hypotenuse, therefore, is the cosecant of 5 pi over 3. And again, that's a right triangle. Seeing no questions, I will move on to number 4, unless anyone has a thought on that. Oh, no, wait, I'm not done. My bad. Sorry. Good save. I'm supposed to choose one of the triangles I drew and use it to explain how a trigonometric ratio can be expressed by the length of a triangle. So this is the big idea in this whole piece. So moving all this over, let's see. Yeah, I'll just write over here. So how about this? We'll say here was my triangle with pi over 6, and this was 1, and this is sine of pi over 6. And I'm going to name this triangle so I can refer to it. Say point A, point B, point C, and this will be side B and side A and side C. Cool. So in triangle ABC, by definition, sine of A equals the opposite side A over the hypotenuse C. In making the hypotenuse C equal to 1, this becomes sine of A equals A over 1. So A, side A, is the sine of A. Thus, by using a unit triangle, the ratio A over C becomes the length A. Wonderful. Is there anyone who was paying attention on the multiple times I have answered that question and can respond to Tomas's question? Is there going to be a final review for juniors? Hopefully someone watching noticed me talking about that. Perhaps not. Yes, Tomas. There is another final review for juniors 1 week from this time, Wednesday, before the 4th period final from 7:30 to 8:30, same as this one. Sweet. Thank you, Grayson, Melissa, and Elizabeth. Much appreciated. Any questions on number 3? Okay. Number 4, graph sine of x, secant of x, cosine of x, and connect the maximum, minima, and zeros of the cosine function with the maximum, minima, and zeros of the sine. Connect the maximum, minima, and zeros of the sine functions with the maximum, minima, and zeros and asymptotes of the secant function. So we're going to do sine of x in red. So the sine curve goes up and down, something like that, and then down and up, something like that. Beautiful. And then I'm going to just copy it to make a blue cosine curve, because the cosine curve is congruent to the sine curve. And I'll just move my blue cosine curve over there. Wonderful. And then I will do a green secant function. And I know that the secant function is the reciprocal of the cosine function. So it's got asymptotes like that, and like that, and like that, and it looks like this, and like this, and like that. Ta-da! Beautiful. And I'll put a scale on here, and I'll say this sine function has a period of 2 pi, and this must be 3 pi over 2, and here's pi, and here's pi over 2, and 0, and negative pi over 2, and, well, that point, which I haven't really lined up particularly well, must be negative pi, and over here, negative 3 pi over 2. And on this scale, I've got 1, and down here is clearly negative 1. Beautiful. And then what kinds of things are we supposed to notice about? We are supposed to notice, and I'm going to do my noticing in purple, that whenever sine is at a 0 point, 0 of sine, then cosine is at either a minima or a maxima. Zero maxima. Suppose I should say maximum. That's a specific one. And here, 0 and min. And same thing the other way around. Whenever cosine is at a 0, like there, 0, then sine is at a min, like that point, min of sine, and it could be a max, like there's a, uh-oh, the blue graph was cosine. What am I doing? Blue graph, cosine. Sorry, red graph, sine. My fault. This was cosine of cosine minimum. Okay, better. Okay, so this was a max of cosine when sine was at a 0. 0 of sine. Cool. So to summarize, for A, maxima, minima, and zeros of the cosine function. So maxima of cosine of x is a 0 of sine of x. Minima of cosine x are, that should say r too, huh? R zeros are also zeros of sine x. The zeros of cosine x are maxes and mins of sine of x. Cool. Then B. How do the maxima, minima, and zeros of the sine function relate to the maxima, minima, and zeros of the secant function? And I actually meant to ask about the cosine and secant because they're reciprocals, and that's more interesting. But that's okay. We'll answer the question as written so no one gets confused. So we'll say that we'll notice that when sine is at a 0 point, secant is at either a max or a min. Zeros, I'll write the word zeros. Zeros of sine x are maxes and mins of secant x. And, whoops, the max and the min of sine of x are asymptotes of secant of x. Any questions on number 4? Seeing none, I'll go ahead and move on to number, I think I might have messed up the numbering when I brought them over here. But anyway, I'm at number 5 here. Hopefully they're just in order. So next one is give a real life example of a correspondence between sets that does not represent a function. Use the definition of a function to explain why it is not a function. So the definition of a function is if there is, so this is a function. If there is exactly one input, exactly one output for every input then a relation is a function. So we want to give a correspondence between sets that doesn't represent a function. So that means we want something where there's not exactly one output for every input. So I'm thinking of a potential relationship where certain inputs have more than one outputs. We used again and again the relationship between fathers and daughters and mothers and children. Let's talk about how about um, the function that assigns to any person their birthday would be a function, but the function that assigns every birthday to a person would not be a function. So we'll say inputs, birth dates, outputs, people born on that day. And we'll say this relation is not a function because any input date, because how about 4? Any input, oh, that was an ugly A. For any input date, there is more than one person born on that day. For example, let's see, I'm going to look at my own birthday. Born on May 9th. Famous people. And I'm finding out that Billy Joel was born on May 9th. For the input. Oh, and Ghostface Killer from Wu-Tang Clan. Sweet. Yeah, also twins. Thank you, Melissa. Twins would show that this was not a function. For the input, May 9th, both Ghostface Killer and Mr. W are outputs. Thus, the relation is not a function. Thank you, Katie. Agreed. Having the same birthday as Ghostface Killer is lit. Oh, we should get rid of that ugly looking speaker over video. That's better. Okay, hopefully there are no questions there. So I will move on to the next one. Uh, Look at a math problem, like a real math problem. How rare is that? State the domain of f. Well, let's see. The domain of f, well, we can't take the square roots of negative numbers. So we can't plug in any x that would make that square root be negative. Let's see. Sorry, pause. We have a question, and it looks like a good question. We use the father, we would say that there's more than one daughter for father. Yes. So let's go back and say two relations. One, input dads, output daughters. So my dad, Steve, has two daughters, Grace and Claire. So this is not a function. But over here, to a different relation, if we input daughters and output dads, then Claire, my sister, has exactly one output, Steve, and Grace, my other sister, has exactly one output, Steve. Therefore, this is a function. From a, strictly biological perspective. Obviously, from a social perspective, many daughters do have two fathers, which would make it not a function. But hopefully we get the idea. Great question, Elizabeth. Did I answer it? Hopefully. So I was back here on number 6, and I was saying that we can't take the square roots of negatives. So we have a domain set x such that x is less than or equal to 5. Because I can take the square root of 0, so 5 minus 5 would make 0. Square root of 0 is fine. And as long as x is less than 5, like maybe it's 4, 5 minus 4 is 1, square root of 1 is 1, no problem. State the range of f. Well, after I take that square root, the smallest number I could get was a 0. So we have an output set y such that y is greater than or equal to 0. And evaluate f of negative 4, where f of negative 4 is equal to the square root of 5 minus negative 4, because I plug in negative 4 for x, which equals the square root of 5 plus 4, which equals the square root of 9, which is 3. Find x such that f of x equals 5. So I want f of x equal to 5, so I want 5 equal to the square root of 5 minus x. So I will go ahead and square both sides. I'd like 25 equal to 5 minus x. I'll take away 5 on both sides for 20 equal to negative x. And I'll say x must be negative 20. I can check my work now and say, what is f of negative 20? Well, it is the square root of 5 minus negative 20, which is the square root of 5 plus 20, which is the square root of 25 which is 5. Check. And find f of negative x plus 2. Is equal to the square root of 5 minus, and instead of x, I'm going to put in negative x plus 2, which means I get 5 minus negative x is plus x, minus 2 is minus 2. 5 minus 2 is 3, so I've got the square root of x plus 3. Cool. This was E, this was D, that was C, A, and B. If there are no questions on number 6, I will move on. Below is a graph of an arbitrary function, g. Well, I didn't give you a graph, so let's go ahead and make one. An arbitrary function, g. I'm going to make g in blue, and g is going to look like that. Beautiful. Here is g. And I'm going to say this was -7 and 1, 2, 3 spaces. That's clearly -4. And over here is 3, and this looks like 4. Again, that was just arbitrary. I made that up so that there was an arbitrary function. Everyone agreed? That wasn't like something you were supposed to know. I just made up an arbitrary function to hopefully everyone gets that. Let me make a note. I made that up. It's random. That's what that means. Cool. Okay. But now we can actually do the problem. G of x plus 5. Oh, I didn't really leave a lot of space for plus 5. But that's okay. Plus 5. We're going to say G of x plus 5. Plus 5 should move up 5. So here we go. Let's go up 5. There's my function g. And h of x is going to move it up 5. So up, oopsie, 1 space. And 2 spaces, and 3 spaces, and 4 spaces, and 5 spaces. So that's now way up here. And let's see, I bet you I can pull that out of the way. There we go. And then if I erase that, and that would be in business. Look at that, I fixed everything. Arbitrary meant that. Plus 5. Okay. Cool. And we're extending this graph. So here's h, and it's now up 5 spaces. So if it was down at 3 down there, it's now from 8 to 9. Great. And g, wow, I really didn't leave the right spacing here, did I? Should have looked at the problem ahead of time. So here we go. This is going to be the next one. It is j of x, and that's going to move us left 5. So, oh, I shouldn't have done that. Cool. I group. Now that I've done that, I can say this was left 5. And now I can move this. Let's see. -4 to -7 is left 3 spaces. So 4 spaces, 5 spaces. And scaling over here, extend the graph that way. Oh, in black that way. If I moved it left 5, I must now be at -9 and -12. Great. That looks like pretty good scaling. Perfect. Explain clearly and precisely why the +5 move the graph of h in a positive direction and the graph of j, here's j in a negative direction. So let's see. We want to know in this case that in the graph of h of x, the +5 is added to all the outputs of g of x, making any input x yield an output 5 greater. The y values are increased by 5. The graph moved up +5. Then, let's see. Something I was pointing out to students the other day is that if j of x equals g of x +5, then g of x is equal to j of x -5. So we could think of it as it being this -5 that we're moving to here. That it's this is the minus that moves us that way. I don't know if that helps anybody. But let's see. In the graph of j of x, the 5 is being added to all the inputs of g of x, making any input x 5 less to give the same output y. So this was greater, this was greater, this was less. The x values are decreased by 5. The graph moved left by the vector -5, 0. Here it was 0, 5. Questions on number 7. Okay. Seeing none, onwards. Grayson says he doesn't like it. Thank you, Grayson. It is now 8:30. I'll probably take another 10 minutes or so, do a couple more, but I am gonna start winding down. Does anyone here want me to cover some of the later stuff that I haven't gotten to go over? Is there anything that needs to be covered specifically that you had any urgent questions on? 18 and 22. Let's skip to those. Okay, 18 and 22. And I'm going to pull up my one with my original numbering because I've messed up the numbering. Use the angles. Okay, cool. And uh-oh. Which one was 18? Okay. 18 used to be, there we go. 18 used to be, establishing the trig identity and then the piecewise function. You got it, Elizabeth. Oh, but Melissa wants the Ferris wheel. So let's do the Ferris wheel first. And then Katie wants the inverses. Okay. Katie wants the inverses. Which one does Katie want? Katie, what do you want? Oh, are you talking about number 16, Katie? You're talking about number 15 or number 14 or number 13. There's a lot of inverse ones, Katie. Isn't that eight? Katie says, isn't that 18? 18 was establishing a trig identity. Am I on different numbering than you? I must be. Okay. What do I do to the numbering? Shoot. Okay, here we go. Now I can see which one Katie wants. Now I'm with you. Okay, so Elizabeth said 18 and 22. Melissa says Ferris wheel. And Katie, so Katie wants also 16. Got it. Okay, I think I'm with you guys now. Beautiful. So starting with the Ferris wheel. Ferris wheel is 32 minutes and rotates once every 3 minutes. The center axle of the 20 wheel is 20 meters off the ground. So here's 20 meters off the ground. That's going to be the center. If it's 32 meters in diameter, it's going to go up to 36. And it's going to go down to 4. And we're going to get on the Ferris wheel at the bottom. And then every 3 minutes, it's going to turn over. So here's 3 minutes, and here's 6 minutes. So we're back on the bottom at 3 minutes, and we're back on the bottom at 6 minutes. At minute 1.5, we're up at the top, 36. And at 4.5, also up at the top. Right here, we're at 20. And right here, we're at 20 and 20 and 20. And things are going to go like that, and 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 like that. And we go back up. Beautiful. Okay. There's my graph. So this was A, B. Write a function h that gives the time, height h of t for any time t for passenger on the Ferris wheel. H of t equals negative 16 cosine of 2 pi over 3t plus 20. So here we had half the diameter, the radius of the wheel, radius of wheel. Here was because we start at the bottom. Start at bottom. Here we've got the period. And here we've got the central axle. And the 2 pi is the natural period of cosine x. Okay, and then C. How would I get from cosine of t to h? C. So parent function p of t equals cosine of t. And let's see, I'm going to start by getting this negative in here. So to negative p of t, which would be negative cosine of t. And that negative is a 1. Reflection, reflect p about x axis. And then the next step is I want negative 16 p of t, which is negative 16 cosine of t. And in that step 2, I'm dilating by 16 about x-axis. And then let's see, what would I like to have next? I'd like that 2 pi over 3. So I'd like to get to next step, negative 16 p of 2 pi over 3t, which is negative 16 cosine of 2 pi over 3t. And this step 3 is dilating by 3 over 2 pi about the y-axis. And then lastly, I want that 24. So I'm going to say last step, getting to h of t, which is negative 16 cosine of 2 pi over 3t plus, was 20 plus 20. And step 4 is translate by the vector 0, 20. There's number 8. I think it's 8. About Ferris wheels. Cool. And then Katie and Elizabeth both want number 18, which have messed up the numbers here, but it's, yeah, that one. It's, well, let's see. Katie wanted 16 first. So let's do 16, which is here. That's a nice, easy one. Why did Elizabeth has a great question. Go back. Why did I scale to 36? I saw here that the wheel was 32 meters. So I'm thinking about that wheel, and I'm thinking about it in what color? Thinking about it in this light blue color. And so it's a wheel that looks like, well, let's make it look like that. And we'll keep the scale of the graph, and it goes down here and like here and like here. And this point is central axle, 20 meters. And here, this is 32 meters. And that means that the radius must be 16 meters, half that diameter, 16 meters. And that means that the whole distance off the ground has to be 36 meters. Did I answer your question, Elizabeth? Hopefully. You'll let me know if I didn't. And I have renamed this 13, but I think, Katie, this is the one you wanted, and you had it as 16. I'm pretty sure that was what 16 was. Yeah, on the paper I handed out. Looks like it. So here, I'll X. This is 16. And we want to find the inverse sine of the cosine of 11 pi over 6. Beautiful. Elizabeth says I did answer the question, and Katie says this is 16. Okay, so here's a diagram of, you got it, a unit circle. And I need to go 11 pi over 6 radians all the way around to here. And this is theta equal to 11 pi over 6. just a mere 30 degrees short of 2 pi radians. And the cosine value, well, let's see, the point on the unit circle right here is root 3 over 2 negative 1/2. And the cosine is, of course, the x value. So that right there is the cosine of 11 pi over 6. So because I now know that cosine of 11 pi over 6, just this part is equal to root 3 over 2, I can rewrite this as being the inverse sine of root 3 over 2. Which means my new question is, what angle has a sine value of root 3 over 2? Well, I know that the sine is the y value, so I'm going to go up here to the spot where we've got a sine value of root 3 over 2. And I know that this point is 1/2 root 3 over 2. And that angle to that spot is, of course, theta equal to pi over 3. So the inverse sine of root 3 over 2 is pi over 3. And that's it. Done and done. That's the sine of pi over 3. Okay, that was 16. Both Katie and Elizabeth have asked for 18, which is a rough one. And Elizabeth then also asked for 22, okay, which is a piecewise function. Okay, so given f of x equal to 2 cosine of 3x minus 1, find f inverse of x. So in order to find f inverse, I'm going to say y would equal 2 cosine of 3x minus 1. I'm going to switch the x and the y for x equal to 2 cosine of 3y minus 1. I'm now going to solve for y. I'm going to say plus 1 plus 1. I'm going to say that gives me x plus 1 equal to 2 cosine of 3y. I'm going to divide by 2, which gives me x plus 1 over 2 equal to equal to cosine of 3y. I'm going to undo cosine by inverse cosining. So I've now got inverse cosine over here and inverse cosine over here. So now I've got, switching sides, 3y equal to the inverse cosine of x plus 1 over 2. And I was so close, dividing by 3. I will get, I'll mark here that this is actually 18 on your paper. Dividing by 3, I now get y equal to 1/3 inverse cosine x plus 1 over 2. And that means that I have now found f inverse, which is 1/3 inverse cosine of x plus 1 over 2. Okay. My next task is that I'm supposed to sketch a graph of both f and f inverse below. And then I'm supposed to use f inverse to solve the equation 2 cosine of 3x minus 1 equals 0. So in order to sketch the graph, I'm going to go ahead and make a table. So table x's. And then after the x's, I'm going to want to know what are the 3x's. And then after the 3x's, I'm going to want to know what are the cosine of 3x's. And then I'm going to want to know what are the 2 cosine of 3x's. And then I'm going to want to know what are the f of x's, which are the 2 cosine of 3x's minus 1's. Cool. And I would like, let's see, I also want to use the same table to graph the inverse function. So that means I'm going to want it to be on the domain for which cosine is invertible. I know that the domain that cosine is invertible is on the domain from negative pi over 2, no, sorry, 0 to pi. Cosine is invertible on 0 to pi. So I'm going to say 0 pi over 2, and over here pi, and here will be pi over 4, and 3 pi over 4. Okay, and let's see. Oh shoot, I put those all in the wrong spot, didn't I? Those are my 3x values. 0 pi over 4, pi over 2, 3 pi over 4, pi. So 0 pi over 12, pi over 6, pi over 4, pi over 3. And the cosine of 0 is 1. And the cosine of pi over 4 is root 2 over 2. And the cosine of pi over 2 is 0. And the cosine of 3 pi over 4 is negative root 2 over 2. And the cosine of pi is negative 1. And 2 times that makes 2. And root 2. And 0. And negative root 2. And negative 2. And minusing 1, I get 1. And negative 1. And negative 3. And let's see, root 2 is about 1.4, so 0.4. And negative root 2 is about negative 1.41, so negative 2.41. Okay. And now I need a graph. So I'm going to plot, first of all, inputs and outputs. This is a graph of f of x. So 0, 1. And pi over 12.41. And pi over 6, negative 1. And negative 2.41. And negative 3. So let me put in a scale here. This was 0. And I'm going to zoom in to make this pi over 12. And this was pi over 6. And here I was at pi over 4 and pi over 3. Jackie and Elizabeth are confusion. I was worried about that. So, is the table confusing? Is the function confusing? Grayson, I'm guessing that's a confusion face also. On the table part. Okay, thank you, Elizabeth. That was helpful. So we feel good about finding the function and its inverse. Grayson or Jackie, is this the problem for any of you? Grayson agrees, table. Okay, hopefully it's the same for Jackie. So let me zoom in on the table. So I began here in the table. And I use the values 0 to pi because that's the domain upon which cosine is invertible. So if I'm going to graph the inverse function, I'd really like to have just the invertible part. To get back to these ones, I divided by 3 because I wanted to undo the 3x to get back to x. Then to go here, I just took the cosine values. Then I times by 2, and then I minused 1. And that was it. Don't you do the opposite to find the table values, says Katie. I think that's a good question, Katie. Can you be a little more clear? What opposite do I need to do? I think you're saying here, this is an opposite, right? This was a 3 times x, and I divided by 3 to get back to the x value. Is that what you're pointing out, Katie? I used these inputs to start with. I first set the argument to 0 to pi, and because the argument of cosine was 3x, I wanted the 3x to equal the values between 0 and pi. And then, like Katie's pointing out, since I've decided on what 3x should be, if I want 3x to be 0, then x is 0. If I want 3x to be pi over 4, then x would have to be pi over 12. And I got that by dividing by 3. If I needed 3x to be pi over 2, then I had to make x be pi over 6, and I got that by dividing by 3. To make 3x be 3 pi over 4, then I had to make x be pi over 4, and I got that by dividing by 3. And to make x be pi, oh, sorry. I had to make x be pi over 3, and I got that by dividing by 3. But then apart from just this step, I didn't do any other opposites, right? Here I'm just taking the cosine, then timesing by 2, then minusing 1. Have I explained the table any better? Grayson, you feel like you understand it? Katie, Jackie, Elizabeth? Any luck with the table? Or any questions that are more clear that I can help with on the table? Anyway, I'm going to go ahead and finish the problem. Maybe we'll come up with better questions. I'm now going to graph in red the inverse function. So the inverse function uses the y values as inputs and the x values as outputs. The inverse will go from this input to this output. So I'm going to plot 1, 0. So let's see. 1 is like pi over 3, a little bit less, right? So 1, 0 is right about there. And then I'm going to plot 0.41 pi over 12. So 0.41 is that was a half, it was right there. So 0.41 got to be a little bit less than pi over 6 probably. So 0.41 and up pi over 12. So like there. And then I need to graph pi over 6. So negative 1 pi over 6, negative 1 pi over 6, like there. And negative 2.41 pi over 4. Still should be less than 1, huh? So like that. And negative 3 pi over 3. So this isn't particularly good because my scale is a little funky, but it looks something like that. Sorry, a little touch up here. There we go. There we go. Okay, and this red graph is the inverse function. And it's too bad that I made the x-axis scale different than the y-axis scale because it means these two functions don't really look very nice. So let me pull it up in Desmos just so we can see what it kind of ought to look like a little better. Because it would be nice if we could see the relationship between inverse functions clearly. So in Desmos, it would be, here's the original function, 2 cosine of 3x minus 1, and then the inverse, which we found to be 1/3 inverse cosine of x plus 1/2. So here's what I kind of had for you guys, because I also had the graph kind of scaled out, but that looks real nice. And what we're trying to see is that if we only graph this one on this domain from 0 to pi/3, just the domain on which it's invertible, 0 less than or equal to x less than or equal to pi/3. Then here we go, we see this nice reflective symmetry. And we notice that this graph is a reflection about the line y equals x. That's real pretty. Okay, on this problem, I have one more step. Use the inverse function to solve the equation 2 cosine of 3x minus 1. So here the idea is that you should know that 2 cosine of 3x minus 1 equals 0. Well, this is just the point that this equation f of x equal to 0. So you should be able to solve f of x equal to 0 by saying x is equal to the inverse of 0. And in order to find the inverse of 0, I will say that f inverse of x is equal to 1/3 cosine inverse of x plus 1/2. So that means I'd like to know what is f inverse of 0, which is 1/3 cosine inverse of 0 plus 1/2, which is f inverse of 0, so 1/3 cosine inverse of 1/2. The inverse cosine of 1/2 is the angle for which the cosine is 1/2, which is pi/3. Inverse of 0 is equal 1/3 times pi/3, because pi/3 has a cosine of 1/2. So f inverse of 0 is equal to pi/9. So x equals pi/9. That one's quite the problem. Anything I should go over in more detail there? Oh, I got a thumbs down for that one, huh? Oh well. The last one that was specifically requested. Let's see. I covered the two Katie wanted. I covered the one Melissa wanted, and Elizabeth said 22. So 22, the graph of the piecewise function. So that was this one. Cool. And here I've got, let's see, again, I'm going to make a table. I'm going to have x values. And let's see. I'd like at least some x values between negative 2 pi and negative pi. So I'm going to pick negative 2 pi and negative 3 pi over 2 and negative pi. And then I'd like some x values between negative pi and pi. So I'm going to pick like 0 and pi. And then I'd like a couple x values between pi and 2 pi. So I'm going to pick like 3 pi over 2 and 2 pi. So these ones are going to be sine of x. And these ones are going to be, going to be negative cosine of x over 2. And these ones are going to be in negative sine of x. Okay, so sine of negative 2 pi is 0. Sine of negative 3 pi over 2 is negative 1. And sine, oh, sorry, no, it's not, it's positive 1. Sine of negative pi, just for reference sake, if it was in the sine curve, it would be 0, but it's not actually in the sine curve. And so the I've got the negative cosine of negative pi over 2, and the cosine of negative pi over 2 is also 0. So it's 0 if I plug it into sine of x, and it's also 0 here if I plug it into negative cosine of x over 2. Then I want negative cosine of 0 over 2, which is negative cosine of 0. Cosine of 0 is 1, so we're talking negative 1. And then I'm just wondering, if I plugged pi into negative cosine of pi over 2, the cosine of pi over 2 would be 0. So if I plugged it in on that blue curve, it would be 0. But it's not going to be plugged in the blue curve. It's going to be plugged in the green curve. Sine of pi is also 0, so it is 0. And then negative sine of 3 pi over 2. Well, the sine of 3 pi over 2 is negative 1. Negative 1 is 1. And the sine of 2 pi is 0, so negative 0 is 0. So all of these match up. These are all continuous. Because of this, this is continuous. Because sine of 0 equals negative cosine of, oh, sorry, my fault. Sine of negative pi is equal to the negative cosine of negative pi over 2. And again, here, this is continuous because the negative cosine of pi over 2 is equal to the negative sine of pi. So neither of these have discontinuities. It's continuous here, and it's continuous here. There's going to be no jumps when we switch from this definition or when we switch from that definition. Nice, continuous piecewise function. Okay, so now let's sketch a graph of it. 1, negative 1, negative pi, negative 2 pi, pi, 2 pi. So we've got 0. Okay, red part first. Red part up to 1, down to 0. Cool. And then it switches to the green part here, and it goes green part down to negative 1, up to 0. And it switches to the, oh my bad, that was the blue part, huh? Blue part, blue, red, green. To negative 1, up to 0. And then it switches to the green part for the end. So it's green part there, up to 1, down to 0. And this is the graph of f of x. Cool. Any last dire questions before I'm done? Doesn't sound like it. So I will bid you good night and good luck tomorrow. Hope that was helpful. I'll see you. Well, I'll see you all sometime tomorrow, in the morning or the afternoon. You are welcome, Elizabeth. See you all later.